career very briefly. Then I will probably give you some examples of what research I do. Okay, let's put the laser. Okay, so I am at Southampton at nCATS. I'm currently a professor in Tribo-Sensing. So don't worry about the title at the moment because I'll explain that in a minute. So I've been working there for more than 20 years. I joined Southampton in 2001. So it's been over 20 years I've been doing tribology. But if you look back what I did in my degree, master, and PhD, it was nothing related to tribology. So I had, in a million years, I never thought that I'd be a tribologist, to be honest. But saying that doesn't mean that I'm not enjoying what I'm doing. I really, really enjoy what I'm doing now. But just to give you some background, I did a bachelor degree in chemistry in China at one of the top universities in China, nCATS University. Followed that, I did a master degree, which is also for 3 years in catalyst chemistry. After I finished my master degree, I actually worked at Environmental Bureau, the Research Institute, so that I came across, in research in environmental engineering. So I thought I'd like to, to probably do more study in environmental engineering. That's why I came to the UK in 1996 to study environmental engineering for 1 year. I'd always wanted to do a PhD, so followed that I went into doing PhD, which it was strange because it was about wastewater treatment, which is related to my master project, but then it was more focusing on wastewater treatment plants, that like the pumps monitoring rather than the wastewater treatment processes. So I went into that knowing nothing about sensors, but over 4 years of the PhD, I actually learned a lot about sensors and became very interested in sensing techniques and monitoring, health monitoring for plants and rotating machines. So when I was looking for a job, I found this postdoc at Southampton, looking for someone that could look at the sensing for bearings, which was sounded very related to what I was doing in my PhD. So I applied for it and I got it. Then I realized it was more on the tribology of bearings than the monitoring of the bearing, although it was both. So Tribo-Sensing basically is the combination of tribology and sensing techniques. So over the last 20 years, I started with knowing nothing about tribology and gradually became more and more interested and developed my career in tribology. And in the meantime, I never lost my chemistry and sensing side of interest either. So that's why in 2017, when I became a professor, I defined my title as Tribo-Sensing, which is a combination of tribology and sensing, basically. So at Southampton, I started as a postdoc, as normally what you would do. Then gradually I became a lecturer and associate professor and a professor, all in tribology. In 20 years ago, tribology wasn't as popular, probably. I mean, even now, probably is not as common as people would know as mechanical engineering. But my background, didn't even have mechanical engineering background. So it was totally an unexpected career path to become a tribologist. But I had grown to really like and interested in the research related to tribology. And my main research interests are in obviously tribology and sensing, but mainly focusing on bearings. So including rolling element bearings and also sliding bearings. So in the contact, we looked at pure sliding, pure rolling, and also slide roll, both combined in rolling element bearings. So for bearings, I have looked at their lubrication problems, their lubrication lubricants and lubrication problems, and also look at the friction in bearings, wear and failure modes in bearings. And also in terms of sensing, I have looked at developing new sensing techniques for bearings, including lubricant aging detection using thick films, and also the common techniques like vibration, temperature, and electrostatic sensor is one of the main techniques I've been looking at in bearings as well, for both the lubricant and debris, wear debris monitoring. So apart from the sensing techniques development, I also looked at health state detection methods using algorithms or using signal processing techniques and using artificial intelligence or machine learning techniques. So all in all, really, I have been really focusing on developing integrated, smart or intelligent bearings for various industries. So that's an overview of my research areas. So I've done other things as well, but these are the main things I've been doing over the last 20 years. So my projects are, most of them are actually funded or related to industry. So like bearing manufacturer John Crane funded one of the PhD projects looking at tilting pad bearings modeling for texturing surfaces, and also looking at different materials for the US synthetic bearing company. So the major, many of my projects are sponsored by Schaeffler in Germany. So they are one of the largest bearing manufacturers in the world. Also, my work have been sponsored by lubricant manufacturers and additive manufacturers, OEMs, and also sensor manufacturers. So all the research is closely related to industry problems. So although I have done so many things for today, I wanted to share with you one of my main research areas related to microstructural alterations in bearing steels and rolling counter fatigue. So these topics have been studied at Southampton in my group for over 10 years now. So we have started from looking at just white-edging cracks, and then gradually moved out to all different types of microstructural alterations. As I said at the beginning, my career path, I didn't have any mechanical engineering background. So looking at those microstructure alterations was also a very big challenge for me, because I didn't have a materials background, like a material microstructure background. So over the last 10 years that we have developed loads of unique results, and I'm very proud of my students, my postdocs, and working with all the colleagues as well. So I just wanted to share with you an overview of what we did in this area. Nothing is like to give you some groundbreaking sort of conclusions or anything, just to share what we did to tackle this particular problem in bearings. So I just wanted to go back to start looking at rolling element bearings, obviously related to rolling contact fatigue. It is the phenomenon that's occurring in rolling sliding contact. These happens in wheel on roads or even on rail, and also in all the rotating machines where you have bearings, rolling element bearings, and also gears. So they are caused by cyclic loading on materials. So I like to use this animation because it is so good to show the rolling element bearing and their operation. So if you look at one part of the bearing, for example, this part on the outer ring of the bearing, so every time a ball passing it, it would apply a load to this point, and then leaving it. it is not continuous load, but it's like a cyclic load applying to a material. This cyclic loading often leads to material degradation. So it is the ultimate failure mode for rolling end bearings. So this deterioration of material in rolling end bearings always started with some sort of structural change, or we call it alterations. And then gradually it leads to damages and failures of bearings. And often it involves in crack initiation, formation, and propagation as well. Rolling contact fatigue can cause failures in rolling end bearings, but it is the ultimate failure mode for rolling end bearings. If the bearings are operated properly and lubricated properly, they can last very long time. So the expected bearing life is over 20 years. For example, for megawatts of wind turbine, the main shaft bearing normally rotates at less than 20 RPM, and it is expected to serve more than 175,000 hours or 200 million cycles under the continuous operation, or over 100 million cycles if they operate at 12 hours a day. So this is what we expect, but as most of people have heard that some megawatts wind turbine gearbox bearings fail very early stage, in the very early stages of their operation, rather than servicing for a very long time as they were expected. So the bearing rolling contact fatigue life can be calculated based on the ISO standard 281, where they take into consideration of the dynamic load ratings seen here, and also the operating load and the type of bearings. So if you know your bearing design and you know the dynamic load rating, which is normally you can get from the bearing catalog, you can calculate under the particular operating load that bearing is used in a machine. You can work out their expected life. So L10 is that the number of cycles or hours, 90% of the same bearings would survive without a failure. So if you wanted to work out at L50, that means that 50% of the same bearings will survive without a failure, which is much longer than the L10. The dynamic load rating is calculated, is tested based on that the bearing is has a stationary outer ring, and the inner ring can endure a load that until failure at the rate life of 1 million cycles. So if the bearing can survive for over 1 million cycles under this load, then that's not survive, sorry. So until this load it cannot survive, then that will be the rating life of this bearing. So that's the C for each type of bearings. So essentially, if you know your bearing design, and you could simply work out what's the expected life. However, in real life, in real service life, the bearing life calculation is modified based on two factors. One is related to the coefficient of reliability, and the other one is related to service life coefficient. But these are all derived from experimental, it's not like the standard values for every bearings. So talking about all these about the RCF lives, but really I wanted to show you that how do different microstructure alterations occur throughout the rolling contact cycles. So this is I don't know that I can just flip, okay. So this is a summary produced by Professor at Cambridge in 2012. So he has plotted out this fatigue index versus the rolling contact cycle. graph showing that the different features, including butterflies and the dark edging phenomena and the white edging phenomena, occurring at a different rolling contact cycles. So it's basically saying that butterfly features would occur before 100,000 cycles, and the dark edging phenomena would occur after 10 million cycles, and the white edging phenomena occurs after 200 million cycles. These are only derived based on deep ball bearings and under the contact pressure, maximum contact pressure of 3.43 gigapascals. So of course, there's some limitations of using these data, but it gives you the general trend of what kind of phenomena may occur, or the microstructure alteration may occur during the rolling contact life. This actually agrees with Swan's prediction or summary of the microstructure alteration, including dark edging region, low angle band and high angle band occurring in different regions of revolutions, rolling cycles. So I just give you some definitions of different types of abbreviations. So DR is used to represent the dark edging region. LAB is low angle bands, and HAB is high angle bands. But normally we call it white edging bands to cover both the low angle and high angle bands. I'll show you some pictures in a minute so you know what I mean by different features. So this is what's done in the literature. Just to recap these, so butterfly looks normally like this. You have a center here, which is normally a non-metallic inclusion or voids or some sort of stress razor. And then you can see two wings grow from the inclusion. So we call it, looks like a butterfly. And also the dark edging region normally forms in the subsurface of the material, that this is the top surface of the bearing rays. And this is the band, looking at much darker than the bearing steel itself. So we call them dark edging regions. So reaction of the cyclic loading and material deterioration forming these dark edging bands. And also the white edging bands, including both low angle band, which is 30 degrees towards the surface, and a high angle band, which is 80 degrees towards the surface. So what we have found in the recent study is that the dark edging region can form as early as 5 million cycles, and the white edging bands, including the low angle band, which is occurring just after 100 million cycles, and high angle bands occurring just after 500 million cycles. So these are all from the recent study we carried out. Also, in recent studies that we found the white edging cracks, which is normally lead to an early failure, which it happens a lot in the wind turbine gearbox bearings, they occur much earlier in the bearing life, as early as like 20% of their Elton life, expected Elton life. And these have very different features as the high angle band, low angle bands, dark edging region, or butterflies. So they are networked white edging cracks. Most recently, what we found, another type of white edging cracks, we call it orientated white edging cracks. So they are white edging cracks, but they are basically, they have white edging areas bordered the cracks, but they are more like defined angles to the surfaces, normally 45 degrees to the surface. And they also lead to early failures of bearings. So we have found all these different types of features, and they all have their own impact on the bearing rolling kind of fatigue life. So some of them lead to early failures, like the white edging cracks and orientated white edging cracks. Some don't, like the butterfly, dark edging region, and white edging bands. Apart from the dark edging regions, which is also an alteration, microstructure alteration, but it doesn't have. The others all have what we call white edging areas. So if you look at them, they all have this white sort of structures in these features. So these features appearing to be white because they have what we called nanocrystalline ferrite grains, because they are very small grains and they are harder than the surrounding matrix or the steel structure. So when you polish them and etch them, they remain as very strong material. They are not being etched away. So that's why they appear to be white under the optical lights. So I'm going to focus on these structures for the rest of the talk. So if you compare the appearance of these structures, so I deliberately put from the left to right as strike cycles, so that the appearance in the life of the bearing. I have to clarify that the occurrence of the sequence of occurrence between butterfly orientated white-edging cracks and white-edging cracks are not 100% clear. It's not like that. That butterfly will definitely appear earlier than orientated white-edging crack and white-edging crack, but they're probably similar. They're all appearing very early stage of bearing lives, but they are all earlier than dark edging region and white-edging bands, while the low angle bands occurs earlier than the high angle bands. So in 2D, they all look very differently, as you can see, but in 3D, it's more interesting. So even with the whitening bands, although people have seen that like bands in the subsurface, this is a circumferential cut. So in the circumferential cuts, you see those angled band to the surface. But in the axial direction, there appears to be parallel bands. So in here, showing a 3D of the whitening bands. So these are the low angle bands at 30 degrees. So these are the high angle bands, which are the 80 degree, high angle band at 80 degrees. So they are not just strips, they are actual plates going into the thickness of the ring. So it looks like networked bands in the material. So this is, again, is the first time ever that people have shown the 3D structure of the white-edging bands. Dark edging region, people are probably more understanding that they have a sickle shape in axial direction. So they look like a sickle, thicker in the middle of the contact region, but towards the edge of the surface is thinner. But if you look at in the circumferential direction, they are just look like a band. It depends on where on the thickness on the ring you're looking at. The thickness appearing that bands is different. So, for example, if you're looking at the contact center, it's thicker, but if you look at the edge, the thickness of the band becomes thinner. The white edging crack in 3D, they are looking at networked cracks with white edging area bordered. In the axial direction, again, looks very similar to the white edging band. They look like a parallel bands, but if you look at a circumferential direction, they are like branched cracks. So also recently we have found, this hasn't been published yet, but we are in the process of writing this up. So we found that butterflies, although in all literature been showing that butterflies look like you have a center, you have two wings, even some people have presented in modeling that 3D as a dumbbells shaped, but they actually look like a donut shape. So in the center, you have the inclusion, and then you have the white areas surrounding it. Depends on which stage the butterfly was forming. You could have the whole inclusion encapsulated by the white area or not. Just to clarify, the gray is the white area, which is this, and the white is the inclusion, and the red are the cracks and the voids. We also look at the orientated white edging cracks. So these white edging cracks are much, much bigger than butterflies. So in the probably over 100 micrometer of length. So this is only part of one of the orientated white edging cracks we had been able to analyze. So this is only show it's a very similar structure as this, but we're only showing to one slice of that material, that feature. So you can see that also the blue is showing the white area, the red is showing the voids. But we weren't able to capture an inclusion in this, but we assume there will be inclusions in the orientated white-heading crabs. So just to show that in 3 dimensions, they could be totally different, as you could see in the 2D that most people have been looking at. Also, in terms of the microstructural constituents in those different features, we found that there are 2 main constituents, we call it equal-axed and elongated grains. So they are all nanograins. And so these ones, as you can see from the CAMAP, the EBSD CAMAP, that they are rounded sort of grains. This is an SEM BSE image. So you can see these are the equal-axed grains, and these are elongated grains, so they are longer. They're not just globular grains. So this is for the white-heading crab. For one of the white-heading crabs, you can see the 2 different types of nanograins in here. And these are for one of the labs, so low-angle bands structures. So you can see they also have the elongated grains. Sorry, the equal-axed grains and elongated grains. Okay, so in both structures, you can see the 2 different types of grains in their microstructure. For the butterflies and the orientated white-heading crabs, we found that they only have equal-axed grains at different sizes, but we rarely see elongated grains in them. So they are slightly different from the white-heading crabs and the white-heading bands. So with the equal-axed grains, we also separate them into different sizes, and we call them fine grains. So they typically would appear to be very, very wide and very fine structures. So for these, we define them below 50 nanometer in diameter of the grains. And we also have slightly darker appearance grains, so the equal-axed grains. They are we call moderate between 50 and 100 nanometer size, and coarse grains between 100 and 300 nanometer sizes. So to summarize, for the 4 features, butterfly, orientated white-heading crabs, and the white-heading bands, we found that for butterfly, orientated white-heading crabs and white-heading crabs, so they all have fine grains, which appears to be very white, and also they have, most of them have the moderate grains, which can be white or slightly darker, depends on what you have on the surface. For the white-heading crabs, also have some coarse grains, which is less common, so they're not the most. So you can see here, most of them are fine grains and moderate grains, but the coarse grains are very small amounts. But all of the 3 have elongated grains, but they are not so many comparing with the white-heading bands, as I showed you earlier. So for the white-heading bands, the most grains are the coarse grains and the elongated grains. Also for the white-heading bands, they have what we saw called lenticular carbides. So as you can see this micro SEM image here, so we have the elongated grain here, we have the equal-axed grains there, and also we have this very fine structure here, we call it lenticular carbides. All the mechanisms of these features formation we have discussed in all the publications, so I'm not going to bore you with that in this talk, but just to show you the fun things. Also, we looked at the influence of cracks in these features and their impact on bearing life. So what we found, those features like the dark hedging region, which have the small bands here, and also the low angle bands and the high angle bands here, they don't have cracks. So we did loads of detailed analysis and found that they don't have cracks, and they don't lead to early surface damages either. with the white-hitting cracks and oriented white-hitting cracks, we found they both have very obvious cracks in the structure, and both of them lead to early surface damages and even early bearing failures. With butterflies, it was a bit strange because butterflies, some of them have cracks in the wing. You can see here, very obvious crack in the wing and here, but some of them don't have cracks, like this wing. We don't see any cracks in the wing, or major cracks as we normally call it. And butterflies don't normally lead to early failures as well. We tried to find out why. So we did some analysis with the voids or crack versus the whitening area volume analysis using the 3D images we obtained for one of the oriented whitening cracks and one of the butterflies. So we found that for the oriented whitening cracks have appeared to have large amount of cracks. So those red, the red is for the voids, blue is the white area, and white is for the inclusions. So you can see this oriented whitening crack has a lot of voids in there, comparing with the butterfly, only have a very small amount of voids in there. So we did some analysis, quantified them, and found that the ratio between the voids and the whitening area for the butterfly is much less than the oriented whitening cracks. And also we found that we compared the different stages of butterfly formation and found that as the butterfly forming develop, the ratio between the void and whitening area actually reducing. So that's probably why butterflies don't lead to failure, because they have less cracks in development as comparing with the oriented whitening cracks. So that's probably giving us some sort of suggestions why some of these features lead to early damage and failures, some don't. So based on these analyses, we just basically, we conclude that the oriented whitening cracks have much higher the void to whitening area volume ratios. That's why they lead to non-arresting crack formation and growth, and then lead to the early failures. With the normal butterflies, we're not considering very large butterflies, which we know they lead to early failures. So they have much lower values of the ratios. So that's why they arrest and they don't lead to failures. We expect that whitening cracks would be similar values or different, similar phenomena to the oriented whitening crack, but unfortunately we haven't done these kind of analysis. It is quite time consuming and very difficult to get all the details. So this is ongoing. So we're expecting we get some sort of conclusions on whitening cracks, which is the topic of interest to many people.
Professor Wang, oh, sorry, you were just saying, that's okay. Go ahead.
Sorry, I can't see the time, so I'm sorry, I've gone over a little bit. Just wanted to acknowledge my students and postdocs and colleagues at Southampton who had contributed to the work. Especially Dr. Mustafa Ali, he has done fantastic work with gathering all the 3D images and things. And also my sponsors, companies, and Henry Royce and Aachen University did a lot of analysis for us as well. So I wanted to thank them. So I just leave you with these 3D sort of videos to show the high angle bands, the whitening cracks, and a butterfly here, and also the oriented whitening cracks these. So you can see how they look in 3 dimensions. And thank you very much.